Previously, we learned how to reason about the flow of primitive data, such as integers, in a computer program. In this lesson, we will learn how to reason about the flow of non-primitive data, better known as pointers, objects, or references. This sort of analysis of a program is called a pointer analysis. Pointers are prevalent in mainstream programming languages like C, C++, Java, and even Python. Therefore, pointer analysis is fundamental to any static analysis for reasoning about the flow of data in programs written today. By the end of this lesson, you will have learned what pointer analysis is capable of doing and how you can incorporate it into your own data flow analysis. Let's begin with a data flow analysis for an example program without pointers. Just two integer variables, x and y. Notice that this program can be expressed in the while language that we introduced in the previous lesson, though we'll extend that language with the Boolean operator equals for the sake of clarity. Suppose the goal of our data flow analysis is to prove the assertion that y equals 1 at the end of this program. We can perform a forward must analysis for this purpose. It begins by analyzing the assignment to x and infers that the value of x at this program point must be 1. It then analyzes the assignment to y and infers that since the value of x before the assignment is 1, then the value of y after the assignment must also be 1. The analysis thus proves that the assertion y equals 1 is valid at this point in the program. Now let's slightly change this example to use pointers. Besides assignments, we see three new kinds of statements here, which we will need in order to meaningfully talk about pointer analysis in this lesson. Let's look at each of them in turn. In the modified program, the first new type of statement is the object allocation statement, which uses the keyword new. Much like in C++ and Java, this statement allocates memory for a new object of type circle and then sets x to be the location of that allocated section of memory. An object can have fields which we can read from and write to. In the statement x.radius is assigned 1, we access the memory allocated to the circle that x refers to, and then we access the portion of that allocated memory dedicated to the radius field of the circle object, and then we write the integer 1 to that space in memory. This operation is called a field write. By contrast, in the following statement y is assigned x.radius, we access the memory allocated to the circle that x refers to, then we read the integer in the section of memory dedicated to the radius field of x, and then we copy that integer to another location in memory which stores the value of variable y. This operation is called a field read. Now let's perform our analysis on this new program. We begin by analyzing the assignment to x.radius. We can infer that the value of x.radius at this program point must be 1. We then analyze this assignment to y, and we can infer that since the value of x.radius before the assignment is 1, the value of y after the assignment must also be 1. Our analysis therefore proves that this assertion is valid. Notice that this time our analysis had to track the value of expressions more complex than variables, notably the expression x.radius. Expressions built using pointers such as x.radius allow the same memory address to be referred to in different ways. This situation is called pointer aliasing. The example we just looked at did not have any pointer aliasing since we only had one circle pointer. Let's look at a slightly different example that does have pointer aliasing and see what challenges it poses to our analysis. In this example, we have two circle pointers denoted x and z. But let's not commit yet to what z points to. Also note this additional assignment statement that writes 2 to the radius field of the circle denoted by z. Our analysis proceeds as before. After this assignment, we infer that the value of expression x.radius is 1. But after this assignment, our analysis is stuck. We do not know whether the value of expression x.radius remains 1 or becomes 2? The answer depends on whether or not z is an alias of x. Let's consider the two cases, one in which z denotes a different circle than x, and the other in which z denotes the same circle as x. Here, let's suppose x and z denote different circles. In this case, our analysis proceeds as follows. After this assignment to z, we infer that x and z denote different circles. Continuing further, after this assignment to x dot radius, we infer that the value of x dot radius is 1. Now we analyze the assignment to z dot radius. This time, we conclude that the value of x dot radius remains 1 after this assignment because we track the fact that x is not equal to z. Finally, we inspect this assignment to y and we infer that since the value of x dot radius is 1 before the assignment, the value of y must be 1 after the assignment, thereby proving the assertion. To recap, our analysis was able to prove this assertion by tracking the fact that it is not true that x and z may alias. An analysis that is dedicated to proving facts of this form is called a may-alias analysis. May-alias analysis is also what we call pointer analysis. At this point, you might be wondering, just as we had may versus must data flow analyses, is there a counterpart to may-alias analysis? The answer is yes, and as you might expect, it is called must-alias analysis. To understand must-alias analysis, let's consider the alternative case in our example program where x and z denote the same circle. In other words, x and z are aliased. In this case, our analysis proceeds as follows. After this assignment to z, we infer that x and z denote the same circle. Continuing further, after this assignment to x dot radius, we infer that the value of x dot radius is 1. And after analyzing the assignment to z dot radius, we conclude that the value of x dot radius becomes 2 after this assignment. We are able to conclude this fact because we tracked the fact that x and z must alias. Finally, we look at the assignment to y. We infer that since the value of x dot radius is 2 before this assignment, the value of y must be 2 after this assignment. The analysis thus fails to prove the assertion. Indeed, this assertion is incorrect. The correct assertion should be y equals 2, which is what our analysis also proves. To recap, our analysis was able to prove this assertion by tracking the fact that x and z must alias. May-alias analysis and must-alias analysis are duals of each other. But the technical machinery needed for must-alias analysis is far more advanced than that for may-alias analysis. Also, may-alias analysis is useful for many more practical data flow analysis problems than must-alias analysis. Therefore, in this lesson, we will focus on may-alias analysis, which is also called pointer analysis. Before we dive into how to do pointer analysis, it is worthwhile to look at why we need a separate type of analysis for pointers. This will help make the motivation for the pointer analysis algorithm more clear. Data flow analysis in the presence of pointers is more challenging than data flow analysis in the absence of pointers for a couple of reasons. Let's take a look at the following data structure, a doubly linked list created by this example program. Each vertex is a node object in memory, and each node object has a data field and two pointer fields called next and priv, which are capable of pointing to other objects. A precise data flow analysis of this program would need to keep track of all possible ways of accessing each node's data field. For example, the data field of the node denoted N1 could be referred to in many different ways. One way to refer to it is simply h.data. Another way to refer to it is h.next.priv.data. Yet more ways to refer to it are h.next.next.priv.priv.data, h.next.priv.next.priv.data, and so on. Tracking all these different expressions is inefficient at best and infeasible at worst. In the presence of cycles, like in this example, there are infinitely many ways of referring to the same piece of data. As was the case for data flow analysis in the absence of pointers, the problem of deciding whether two pointers alias is in general an undecidable problem. In other words, there is no algorithm that always terminates and perfectly decides whether two pointers alias. The solution to this problem of undecidability is to sacrifice completeness, just as we did for data flow analysis in the absence of pointers. This means in exchange for the possibility of obtaining false positives, we can design an alias detection algorithm that terminates and never gives false negatives. It is worth being a bit more precise in what we mean by the term false positive. Let's revisit our earlier example. Remember that the question we are asking in this problem is it possible for two given pointers to be aliases of one another in some execution of this program? A shorthand version of this question is the Boolean function x may alias z. This function returns no if there is no possibility that x and z are aliases, as is the case in this example. Take a moment to convince yourself that this answer enables our data flow analysis to eventually prove this assertion at the end of this program. Conversely, x may alias z returns yes if we cannot determine whether x and z are aliases or not. In other words, yes does not mean x and z must be aliases. It just means they may or may not be aliases. If x may alias z returns yes when x and z are not actually aliases, we consider this a false positive. Let's take a look at how a false positive manifests in this example. Suppose x may alias z returns yes. Then the most accurate information that our data flow analysis can safely infer at this point is that x may or may not be equal to z. Continuing this reasoning, our data flow analysis concludes at the end of this program that the value of y may be either 1 or 2. The analysis thus fails to prove the assertion that the value of y must always be 1 at this point. The conclusion that the value of y may be 2 is a false positive whose existence can be traced back to the pointer analysis answering yes to the question x may alias z when in fact x and z are not aliases. There are many sound but approximate algorithms to the problem of pointer analysis. All these approximate algorithms generate false positives in certain circumstances, but they differ in their precision, that is, their false positive rate. The approximations that these algorithms perform differ in two key aspects: how they abstract program data, in particular dynamically allocated data, which we will call the heap, and how they abstract control flow. We already saw an abstraction of control flow in the previous lesson on data flow analysis, where we approximated all branch conditions in the program's control flow graph using non-deterministic choice. Pointer analyses typically go further in that they ignore control flow entirely and instead look at the program as a set of unordered statements. Let's dive deeper into data and control flow abstractions for pointer analyses using an example program. Throughout this lesson, we will use this Java program to illustrate key concepts of pointer analysis. This program constructs a representation of an elevator. An elevator object has two fields. One field is an array of floor objects representing different floors in a building, such as basement, first floor, second floor, and so on. The other field is an array of events objects. An example event is a person pushing a button for the second floor in an elevator currently on the fifth floor. The doIt function takes as input the number of floors m and the number of events n. It starts out by creating an object of class elevator. It then initializes the floors and events fields of the created elevator object. Let's take a look at a sample concrete run of this program. In this run, we will create an elevator for a building with 3 floors and 2 events. That is, we will assume that the doIt function is called with m equals 3 and n equals 2. When the doIt function is called, the allocation on the right-hand side of this line is evaluated first. This allocation calls the elevator class's constructor method, which we do not show. Having completed the construction of the elevator object, we assign the address of this elevator object in memory to the variable v. In the next line of the program, we first allocate an object array with 3 cells, and then we write the location of this array in memory to the floors field of the elevator object we are constructing. In the next line, the same procedure is repeated, except that now we are allocating an object array with just 2 cells, and we are writing the location of this array to the events field of the elevator object. In the 0th iteration of the first for loop, we take 4 steps. We first allocate a new floor object. We then assign the floor object's memory address to the pointer f. Then we read the floors field of the elevator object being constructed. And finally, we do a field write of the address in f to the 0th cell of the object array at the address contained in the floors field. We then repeat this procedure for the 2nd and 3rd iterations of this loop. Similarly, for the 0th iteration of the 2nd for loop, we do the following 4 steps. We first allocate a new event object. We then assign the event object's memory address to the pointer e. Then we read the events field of the elevator object. And finally, we do a field write of the address in e to the 0th cell of the object array at the address contained in the events field. We then repeat this procedure for the 2nd iteration of this loop. This concludes the operation of the doIt function. This run of the elevator program created only 3 floors and 2 events, but a pointer analysis must be able to reason about each run of this program with m floors and n events for any value of m and n. Pointer analysis achieves this by abstracting the heap. There are many possible schemes to abstract the heap, each of which strikes a different trade-off between precision and efficiency. One of these schemes abstract objects based on the site at which they are allocated in the program. We will look at other schemes later in this lesson. The elevator program has 5 allocation sites, highlighted here. Therefore, pointer analysis operates on the following graph, which conflates all objects allocated at the same site into a single node of the graph. In particular, it collapses all the floor nodes into a single floor node and all the event nodes into a single event node. Instead of labeling the pointers from the object array nodes to these individual objects by array indices, we use the non-deterministic choice symbol asterisk. And also observe that the variables f and e now point to a single node each instead of multiple nodes. The type of graph that this heap abstraction produces is called a points-to graph. In a general points-to graph, there are 2 kinds of nodes: variables and allocation sites. Variables will be denoted by boxes, and allocation sites will be represented by ovals. Since the points-to graph relation is asymmetric, that is, pointers between data need not go both ways, this is a directed graph. So we will represent edges with arrows. There are 2 types of edges in this graph. Arrows from a variable node to an allocation site node will be colored blue, and arrows from one allocation site node to another allocation site node will be colored red and labeled by a field name. Although points-to graphs are finite, it is too expensive in practice to track a separate such graph at each program point. This is in contrast to the data flow analyses we learned in the last lesson, where we tracked a separate set of data flow facts at each program point. Instead, most pointer analyses only track a single global points-to graph for the entire program. They achieve this by abstracting control flow. This particular control flow abstraction that is commonly used by pointer analyses is called flow insensitivity. Applying this abstraction to our example elevator program produces the following abstract program. There are 3 major differences that I'd like to highlight here. First, notice that all control flow features have been removed, including constructs like for loops and also semicolons indicating sequentially ordered statements. Secondly, all statements that do not affect pointers have also been removed. For example, the approximated code no longer has statements setting the integer I equal to 0 and incrementing I. Finally, array indices such as these are replaced by non-deterministic choice denoted by the asterisk symbol. This is similar to how conditions at branch points in data flow analysis were replaced by non-deterministic choice. This abstraction can be thought of as turning the program into an unordered set of statements. Even though we have written the statements in the rough order in which they appear in the original program, it is better to think about the statements as having no precedence over each other. Even though this abstraction appears to lose a lot of information, we will see later in this lesson that it is still able to prove interesting properties, such as the property that the variables e and f do not alias. Next, let's see how a pointer analysis algorithm builds a points-to graph for an arbitrary program. The pointer analysis algorithm follows a similar pattern as the data flow analyses we saw earlier, so we again call the algorithm a chaotic iteration algorithm. We begin by starting with an empty points-to graph. We take the set of statements obtained earlier by applying the flow insensitive approximation, and we iterate through each statement in this set, applying the rule corresponding to that statement to the points-to graph we are building. We continue applying these rules until we iterate through the entire set of statements without making any changes to the points-to graph. At that point, we terminate the algorithm. Now, this is a basic algorithm for pointer analysis, and it sweeps many implementation details under the rug. In practice, pointer analysis algorithms will use a more efficient traversal of statements. They will also employ data structures that make it efficient to update the points-to graph. For pointer analysis, it suffices to consider the following kinds of statements. These statements are similar to those you might find in a Java program. The first is an object allocation statement which assigns the address of a newly allocated object in memory to a pointer-typed variable v. The second is an object copy statement which copies the contents of one pointer-type variable to another. In other words, we are writing the memory address stored in v2 to v. The third is a field read statement which reads the contents of a pointer-type field f from some object, here referenced by the pointer-type variable v, and stores those contents to another pointer-type variable v2. The fourth is a field write statement which writes the contents of a pointer-type variable v2 to a pointer-type field f of an object, here referenced by the pointer-type variable v. Additionally, we can do a different type of field read by reading the contents of some cell of an array of pointers and store those contents to another pointer. Likewise, we can do a different type of field write by reading the contents of some pointer-type variable and writing those contents to some cell in an array of pointers. At this point, you might be wondering whether the grammar we just presented is sufficient to represent all the operations that we might need to reason about in order to determine whether two pointers may alias. The answer is yes. We will not give a formal proof of this fact in this lecture. We will, however, show some examples of how to break down more complicated statements into compositions of these 6 simpler types of statements. First, let's consider the following statement from our elevator program. This statement starts with an allocation of an object array, and then it assigns the address of the newly allocated object array to the field events of the elevator object. We can break this statement down into 2 separate operations. First, we allocate the new object array and assign its address to a pointer type variable which we'll call temp. Notice that this statement is of the form of the first of our 6 simple operations. Then, we'll assign the address stored in temp to the events field of the elevator object. Notice that this statement is a field write, our 4th kind of simple operation. Here's a second example statement. It performs a read of the events field of the elevator object, and then it assigns the contents of E to some cell in the object array that v.events points to. We can again break this statement up into 2 separate statements of the forms shown above. First, we have a field read operation assigning the contents of v.events to the pointer variable temp. So temp now points to an array of pointers to objects. Then we assign the contents of E to a non-deterministically chosen element of this array. We have now broken the compound statement into 2 simple statements of the form specified in our grammar. Here's what happens if we apply these decomposition rules to all of the statements in our elevator program. Like we saw in the first decomposition example, each of these two statements is decomposed into an allocation and a pointer-based field right. The statements V is assigned new elevator, F is assigned new floor, and E is assigned new event are already in forms specified by the grammar, so we don't modify them. However, we modify each of the remaining statements. Likewise, we modify the assignments to the array cells of v.floors and v.events using the pattern we saw in the second example previously. Let's do a quick quiz to check your understanding of the form of programs that we'll be using for pointer analysis, which we will call a normal form. For each of these two statements, fill in the box on the right with equivalent statements in the normal form specified by this grammar. Note that you may need more than two simple statements to capture the entire compound statement. Let's look at some example solutions. Your answers might not look exactly the same, but they should have the same patterns. For the first statement, v1.f is assigned v2.f. We first read the field f of v2, and then we write the contents of v2.f to the field f of v1. Therefore, we need both a field read statement and a field write statement to capture this entire operation. I'll first assign the contents of v2.f to temp, and then I'll assign the contents of temp to v1.f. For the second statement, v1.f.g is assigned v2.h, we'll need more than two simple statements. We need to access the contents of v2.h, so that will be the field read operation temp2 is assigned v2.h. We also need to access the contents of v1.f in order to reach g, so that's another field read operation, temp1 is assigned v1.f. Finally, we need to write the contents of v2.h, which is represented by temp2, to the field g of v1.f, which is represented by temp1. We do so using a field write operation, temp1.g is assigned temp2. By now, you should be convinced that we can take a program written in a simplified Java-like language and express its pointer operations using the 6 simple statements we introduced earlier. In order to perform the chaotic iteration algorithm, we need to create rules to manipulate our points to graph for each of these 6 simple statements. Let's look at the rule we'll apply for the first type of statement, an object allocation. For the statement v is assigned new b, we create a new allocation site node called b. We also create a variable node for v if it doesn't already exist. And then we add a blue arrow from the variable node to the allocation site node. Notice that if there is already an arrow from v to another allocation site node, say a, in the points to graph, we just need to add a new arrow from v to b. This rule, as well as the remaining rules we'll discuss, is a weak update in which we accumulate instead of replacing the points to information, which would be a strong update. This type of update is a hallmark of flow insensitivity. Looking at our example elevator program, let's apply the object allocation sites rule for each object allocation statement. From this first allocation statement, we create an allocation site node for the elevator, we create a variable node for v, and we make the variable node point to the allocation site node. Similarly, we have 4 more allocation statements in this program. Temp1 points to a new object array, temp2 also points to a new object array, f points to a new floor object, and e points to a new event object. Notice that we create separate nodes for the 2 object arrays as they are allocated at different sites. The next rule we'll look at is for the second type of statement in our grammar, an object copy. For the statement v1 is assigned v2, we create a variable node for v1 if it doesn't already exist, and then add a blue arrow from the variable node for v1 to all nodes pointed to by the variable node for v2. Again, note that we do not remove or replace any existing arrows from v1, such as this one. v1 merely accumulates another arrow to b. Our next rule is for field right statements of one of the following forms. In this case, if V1 points to A and V2 points to B, then we add a red arrow from the node for A to the node for B. We then label that arrow by the name of the field, in this case F, or by an asterisk if the field right happens via an array. This reflects the fact that the field F of some object allocated at site A may point to some object allocated at site B as a result of executing this statement in some run of the containing program. If there isn't already a node for V1 or V2, the operation of this rule amounts to skipping this statement temporarily and handling it in the next iteration. Also, if V1 and V2 point to the same node, then the arrow we add will be an arrow from the node to itself. Now let's apply the field right rule to our example program. In the first field right highlighted here, variable temp1 is pointing to an object array, and variable v is pointing to an elevator object. By the rule we just discussed, we add a red arrow from the elevator object to the object array, and we label it floors to match the name of the field being written to. Similarly, for the second field right highlighted here, we add a red arrow from the elevator object to the object array pointed to by temp2, and we label this arrow events to match the name of the field. The latter two field rights in this program are through arrays. However, since the variable nodes for temp3 and temp4 haven't been created yet, we skip these field right operations and we will come back to them in a later iteration. Our next rule is for field read statements of one of the following forms. This rule states that if V2 points to B and B points to C via the field F or asterisk as appropriate, then we add a blue arrow from the node for V1 to the node for C. If a node for V1 did not already exist, we would create such a node before adding the blue arrow. Note that object B may in fact be pointing to many other objects via arrows labeled by the field in question. In this case, we would need to add an arrow from V1 to each of these objects in order to reflect the fact that the field F and therefore V1 may point to any of those objects. If there isn't already a variable node for V2 or an arrow from B to another node via F or asterisk, we skip the statement temporarily and try to handle it in the next iteration. Now let's apply the field read rule to our example program. In the first field read, we create a node for the variable temp3, and then we add a blue arrow from temp3 to the object array to which the floors field of the elevator points to. Similarly, for the second field read, we create a node for the variable temp4, and then we add a blue arrow from temp4 to the object array which the events field of the elevator points to. Now that we have created nodes for temp3 and temp4, we can apply the field right rules to the statements that we skipped previously. Looking at this field right statement, since temp3 points to this object array and F points to this floor node, we can add a red arrow labeled by an asterisk from the object array to the floor node. Similarly, for this other field right statement, we add a red arrow labeled asterisk from the object array pointed to by temp4 to the event node pointed to by E. At this point, iterating through the set of statements again will produce no change to this graph, and so the chaotic iteration algorithm will terminate, leaving us with the points to graph we see here. Now that we have looked at all the rules for pointer analysis, let's return to an example we saw at the beginning of this lesson. Here, we have some code for creating a doubly linked list of node objects. For this quiz, transform this code using the flow insensitive approximation scheme and then perform the chaotic iteration algorithm yourself on the resulting set of statements. What does the points to graph look like when the chaotic iteration algorithm concludes? Click the radio button corresponding to the graph that represents the correct points to graph. The answer for this quiz is the top right graph. Let's work through the example together and see how the chaotic iteration algorithm gets us here. First, we transform the code by applying the flow insensitivity approximation, which results in the following 4 highlighted statements. Note that we didn't highlight the statement h is assigned null. Remember that pointer analysis is a weak update analysis, so we never remove an edge from the graph once we add it in. Instead, the statement h is assigned null just tells us to add no new edges to the node for variable h. So we can safely ignore this statement altogether in our analysis. Now let's proceed through the highlighted statements one statement at a time and build the points to graph iteratively. Applying the rule for object allocation, we create a variable node for v, an allocation site node called node, and a blue arrow from v to node. Let's now look at the statement h is assigned v. Remember that we can iterate through the statements in any order since the statements are coming from an unordered set. Applying the rule for this statement, we create a variable node for h and a blue arrow from h to the node object that v points to. Let's apply the rule for the field right statement v.next is assigned h. Since both h and v point to the same node object, we create a red edge from the node object to itself and label it next. Similarly, for the field right statement h.priv is assigned v, we create a red edge from the node object to itself and label it priv. Iterating through the set of statements again doesn't cause us to change this graph at all, and so the chaotic iteration algorithm terminates, leaving us with the graph we see here as a final points to graph. Thus far, we have looked at a particular pointer analysis algorithm that is commonly used. Recall from the beginning of this lesson that there are many different algorithms for pointer analysis with varying precision. These algorithms can be classified along many dimensions. Let's look at 4 of the most important dimensions and see how the pointer analysis algorithm we learned fits in this classification. The 4 dimensions are whether or not it is a flow-sensitive analysis, whether or not it is a context-sensitive analysis, what kind of heap abstraction scheme it uses, and how it models aggregate data types such as arrays and structures. Flow sensitivity concerns how a pointer analysis algorithm models control flow within a procedure or function called intra-procedural control flow. Pointer analysis algorithms can be broadly classified into 2 kinds, flow insensitive and flow sensitive, based on how they handle intra-procedural control flow. Flow insensitive pointer analysis algorithms, like the one we just learnt, ignore control flow entirely, viewing the program as an unordered set of statements. A hallmark of flow insensitive analyses is that these analyses only generate new facts as they progress. They never kill any previously generated facts. We observed this in the case of the pointer analysis algorithm we just saw, wherein the points to graph only grew in size as each statement of the program was considered. We say that such algorithms perform weak updates. Such algorithms typically suffice for May-alias analysis. That is, it is practical for a May-alias analysis to have a low false positive rate despite being flow insensitive. Flow-sensitive pointer analysis algorithms, on the other hand, are capable of killing facts in addition to generating facts. We say that such algorithms perform strong updates. Such algorithms are typically required for must-alias analysis. That is, it is impractical for a must-alias analysis to have a low false positive rate by being flow insensitive. Another common dimension for classifying pointer analysis algorithms is context sensitivity, which concerns how to handle control flow across procedures, called interprocedural control flow. Pointer analysis algorithms can be broadly classified into 2 kinds, context insensitive and context sensitive, based on how they handle interprocedural control flow. Context insensitive pointer analysis algorithms analyze each procedure only once, regardless of how many different parts of the program call that procedure. These algorithms are relatively imprecise as they conflate together aliasing facts that arise from different calling contexts, but they are very efficient since they analyze each procedure only once. Context-sensitive pointer analysis algorithms, on the other hand, potentially analyze each procedure multiple times, once per abstract calling context. These algorithms are relatively precise but expensive. They differ primarily in the manner in which they abstract the calling context. There are many different schemes for abstracting the calling context that we will study in the next lesson. The choice of the scheme is dictated by the desired trade-off between precision and efficiency for a client of the pointer analysis. While flow sensitivity and context sensitivity concern abstracting control flow, the heap abstraction concerns abstracting program data, in particular dynamically allocated objects, which we call the heap. The heap abstraction scheme specifies how to partition an unbounded set of concrete objects that the program may create in a given run into finitely many abstract objects. Each abstract object corresponds to an oval node in the points-to graph. This partitioning is at the heart of ensuring that the pointer analysis terminates. Much like any of the abstractions we have seen in this course, designing a suitable heap abstraction is an art. Many sound heap abstraction schemes exist with varying precision and efficiency. As a rule of thumb, a scheme that produces too few abstract objects in the points-to graph will result in an efficient but imprecise pointer analysis. Imprecise because it conflates more concrete objects into each of the few abstract objects. On the other hand, a scheme that produces too many abstract objects in the points-to graph will result in an expensive but precise pointer analysis. Let's take a look at 3 heap abstraction schemes that are commonly used. The heap abstraction scheme used by the pointer analysis algorithm we studied in this lesson is called the allocation site-based scheme. This scheme partitions concrete objects based on the site in the program where they were created, called the allocation site. In other words, each abstract object under the scheme corresponds to a separate allocation site. Allocation sites are identified by the new keyword in Java and C++ and by the malloc function call in C. Since there are finitely many allocation sites in a given program, a pointer analysis using this scheme is guaranteed to result in a finite number of abstract objects in the constructed points-to graph. Here is the points-to graph that was constructed using the allocation site-based scheme for our example elevator program. Notice that each of the 5 ovals corresponds to a separate allocation site in that program. Although the number of allocation sites in any program is finite, tracking a separate abstract object per allocation site can be prohibitively expensive for large programs which can contain too many allocation sites, or for clients of pointer analysis that need a quick turnaround time to aliasing queries, such as an integrated development environment, or for situations when it is unnecessary to make distinctions at the fine granularity of allocation sites. The type-based heap abstraction scheme is a cheaper scheme that can be used in such situations. This scheme partitions concrete objects based on their type instead of based on the site where they were created. In other words, each abstract object under the scheme corresponds to a separate type. Since there are finitely many types in a program, a pointer analysis using this scheme is guaranteed to result in a finite number of abstract objects in the constructed points-to graph. Here is the points-to graph that would be computed for our example elevator program by a pointer analysis using the type-based scheme. Notice that each of the 4 ovals corresponds to a separate type in that program, which is indicated inside the oval. In particular, notice that the 2 separate ovals that were created for the arrays of floors and events are now conflated into one, as both have the same type, an array of objects. Yet another heap abstraction scheme is one that does not make any distinctions between dynamically allocated objects, which we will call the heap insensitive scheme. This scheme uses a single abstract object to model the entire heap. Here is the points-to graph that would be computed for our example elevator program by a pointer analysis using the scheme. Notice that it contains a single oval representing the entire heap. Looking at this points-to graph, it should be easy to see that this scheme is highly imprecise for reasoning about the heap, but it is sound nevertheless. So you might wonder, are there scenarios in which this scheme is useful? The answer is yes, for languages with primarily stack-directed pointers like C, where malloc calls are sparse. Pointer analyses for such languages derive most of their precision by reasoning about stack-directed pointers and completely ignoring heap-directed pointers. Of course, this scheme is unsuitable for languages with only heap-directed pointers such as Java. To recap, the three different heap abstraction schemes that we just saw strike a different trade-off between precision and efficiency. As we go from the allocation site-based scheme through the type-based scheme to the heap-insensitive scheme, the pointer analysis gets more efficient, but also less precise. It is important to remember that these are not the only three schemes. There are many other schemes in the literature, and you can even design your own depending on your analysis needs. For instance, there are many schemes that are more expensive and precise than the allocation site-based scheme. These schemes can even make distinctions between objects created at the same allocation site. At the same time, remember that we can never have a scheme that will allow pointer analysis to make distinctions between all concrete objects and still terminate in finite time. Here's the points to graph that we constructed using the allocation site-based pointer analysis. If we ask the question, may the pointers E and F alias? Then we would answer no. This is because the arrows from E to its referred abstract object and from F to its referred abstract object are different nodes in the points to graph. Being in different nodes reflects the fact that the concrete objects referred to by E and F are allocated at distinct places in memory. Therefore, E and F cannot be aliases. On the other hand, if we ask whether v.events of 0 and v.events of 2 may alias, then we answer yes. If we follow the arrows in the graph to find the abstract object referred to by v.events of 0, we would first follow the blue arrow to the elevator node, and then the red events arrow to this object array node, and then the red asterisk arrow to the event node. If we follow the arrows in the graph for v.events of 2, we end up following the same path to end in the same node. Therefore, according to this graph, it could be the case that v.events of 0 and v.events of 2 point to the same concrete object, so we cannot prove that they are not aliases. Note that the concrete objects could be different, but we cannot say one way or the other using this heap abstraction scheme. Now, fill in the remaining boxes in this table answering the question, may the two given pointers alias? Under both the allocation site-based heap abstraction scheme and the type-based heap abstraction scheme. You can see the type-based points to graph we presented earlier in the instructor notes. Let's start by filling in the remaining cells of the allocation site-based column. For v.floors, we follow the arrow from V to elevator and then the arrow labeled floors to this object array node. For v.events, we follow the arrow from V to elevator and then the arrow labeled events to this object array node. Since these two nodes are distinct in the points to graph, v.floors and v.events will always refer to concrete objects allocated at different sites in the program. Thus, they cannot refer to the same concrete object, and so the question, may v.floors and v.events alias, is answered no. For v.floors of 0 and v.events of 0, we need to follow one more arrow each than we did when analyzing v.floors and v.events. We follow the arrows labeled by the asterisks. Since we end up at the floor node for v.floors of 0 and the event node for v.events of 0, we can again conclude that v.floors of 0 and v.events of 0 always refer to different concrete objects. So the question, may they alias, is answered no. Now let's look at the points to graph that the chaotic iteration algorithm generates for the type-based heap abstraction scheme. As before in the allocation site-based abstraction, E and F point to two different nodes. This means that we can be certain that E and F point to objects of different types, and so we can answer the question, may E and F alias, by no. However, we see a difference in the precision of these two analyses when asking whether v.floors and v.events may alias. Following the arrows from V to the elevator node and then the floors arrow from the elevator node, we reach the object array node where v.floor points. But if we had taken the events arrow from the elevator node, we'd end up in the same object array node. Therefore, the type-based heap abstraction scheme cannot distinguish that these two pointers don't actually alias in our example program. And so it answers yes to the question of whether they may alias. Now suppose we wanted to know whether v.floors of 0 and v.events of 0 may alias. We first follow the arrows to the object array node that v.floors and v.events lead us to. Now we need to follow the arrow labeled by an asterisk, but there are two such arrows leading away from that node. So we need to follow both in parallel. All this graph tells us is that v.floors of 0 could point to either the floor node or the event node. And it tells us the same thing for v.events of 0. This pointer could refer to either the floor node or the event node. Since the set of nodes that v.floors of 0 could point to and the set of nodes that v.events of 0 could point to overlap, our analysis cannot prove that they do not point to the same concrete object. So we answer the may alias question as yes. Finally, let's look at whether v.events of 0 and v.events of 2 may alias. Again, following the paths through the points to graph, v.events points to the object array node. And again, since we now have an array subscript to dereference, we take all arrows from this node labeled by an asterisk in parallel. So according to this graph, v.events of 0 could point to either the floor node or the event node. And v.events of 2 could also point to either the floor node or the event node. Since the sets of nodes they could point to overlap, we cannot prove using this heap abstraction that v.events of 0 and v.events of 2 do not alias. So, we answer yes to the question of whether they may alias. Another dimension for abstracting program data in a pointer analysis concerns how to model aggregate data types. These include arrays and records. Let's look at arrays first. A common choice in pointer analyses is to use a single field denoted by an asterisk to represent all elements of an array. Such analyses therefore cannot distinguish between different elements of the same array. The pointer analysis algorithm we saw earlier in this lesson uses this representation. More sophisticated representations make distinctions between different elements of an array. Such representations are employed in so-called array dependence analyses, whose primary goal is to determine whether two integer expressions refer to the same element of an array, much like the primary goal of pointer analysis is to determine whether two pointer expressions alias. Array dependence analysis, in turn, is used in parallelizing compilers to convert sequential loops into parallel loops. Now let's look at another common kind of aggregate data type, records. Records are better known as structs in C or as classes in object-oriented languages like C++ and Java. There are three common choices that pointer analyses use to model records. We will illustrate these three choices using a record type with two fields, F1 and F2. Suppose there are two objects, A1 and A2, of this record type. Then one choice is to use a field-insensitive representation, which merges all fields of each record object. In other words, this representation prevents the analysis from distinguishing between different fields, such as F1 and F2, of the same record object, such as A1 or A2. Another choice is to use a so-called field-based representation, which merges each field across all record objects. In other words, this representation prevents the analysis from distinguishing between the same field, such as F1 or F2, of different objects, such as A1 and A2. The third choice is to use a field-sensitive representation, which keeps each field of each abstract record object separate. Assuming that A1 and A2 denote distinct abstract objects, this representation allows the analysis to distinguish all four memory locations denoted in this table: field F1 of A1, field F2 of A1, field F1 of A2, and field F2 of A2. It is easy to see that this is the most precise of the three representations. The pointer analysis algorithm we studied earlier in this lesson used this representation. Before we close this lesson, let's reflect on the pointer analysis algorithm we looked at during the lesson. Classify it according to the dimensions we just discussed. In particular, is the pointer analysis we discussed flow sensitive? Is it context sensitive? Did it distinguish between different fields of an object? Did it distinguish between different elements of an array? And finally, what kind of heap abstraction did it use? Allocation site-based or type-based? Type in A to mean yes and B to mean no. For the last question, type in A to mean allocation site-based and B for type-based. Now let's review the answers. Is the pointer analysis we discussed flow sensitive? The answer is no, since we used flow insensitivity as an approximation scheme to eliminate the complexity of tracking the points to graph at each program point. Is the pointer analysis context sensitive? The answer is no again. While the example program we used only had a single function, the chaotic iteration algorithm would only analyze each function once without regard to its calling context. Did the pointer analysis distinguish between different object fields? The answer is yes. The algorithm did distinguish differently named object fields, such as the floors and events fields of the elevator. Did the pointer analysis distinguish between different elements of an array? The answer is no. The algorithm abstracted away array elements using an asterisk to represent all subscripts. And what kind of heap abstraction did the pointer analysis use? Allocation site-based or type-based? Although we discussed type-based abstraction later in the lesson, the chaotic iteration algorithm we discussed used an allocation site-based heap abstraction. Let's recap the main topics that we have covered in this lesson. You saw at a high level what pointer analysis is, a procedure for proving facts of the form pointer x and pointer y do not alias. You saw the difference between a may-alias analysis and a must-alias analysis. Since may-alias analysis is less technically demanding and typically more useful in practice, it is what we refer to when we say pointer analysis. You saw what a points to graph is and how it serves as an approximation of the actual state of data during a run of the program. This approximation allows us to conclude a pointer analysis in finite time at the cost of some number of false positives. You also used the points to graph to decide whether two pointers may alias one another. You saw how a particular pointer analysis algorithm, namely the chaotic iteration algorithm, works to build a points to graph for a program. And you learned different dimensions along which pointer analysis algorithms may vary, including whether they remain sensitive to control flow and calling context, the kind of heap abstraction they use, and how they model aggregate data such as arrays and records. With this knowledge, you should be able to implement a pointer analysis algorithm for a simple programming language, and you should be able to determine the costs and benefits of different types of pointer analyses. In this lesson, we presumed that the program we are analyzing consists of a single procedure. Realistic programs, on the other hand, consist of many procedures calling one another. Therefore, any realistic data flow analysis must be able to reason about programs with multiple procedures. Many different approaches exist to extend a data flow analysis from single procedure programs to programs with multiple procedures. In the next lesson, we will learn about these approaches. Following the theme we have seen in this lesson and the previous one, all of these approaches will be sound, but they will strike different trade-offs between precision and efficiency. Which approach to use thus depends on the desired trade-off for the analysis you are designing.